Hello, ladies and gentlemen. Thank you for joining us, spending your time with us today for a Code Talk. If you're not familiar, a Code Talk it's not a recorded session, it's a live coding session. Lucas and myself, we're going to be live coding for you today. My name is Cy Venom. I'm a Principal Solutions Architect with AWS.
Hey folks, nice to meet you all. I'm Lucas Duarte, a Principal Solutions Architect here at AWS as well.
Yeah, and today we're going to talk about how you can streamline EKS operations with Agentic AI. This is very much going to be an informal, casual session. We want to give you folks an opportunity to ask questions at the end as well. We're going to be going back and forth. Lucas and I, we've done this a couple times before, and we're excited to run through what we built for you today. Last year, we did a similar session about using AI. You know, this was before the time of agents. This is even before MCP was getting popular. So we built a lot of things from scratch. This year, we leverage tools that are available out there that make it even easier to build really robust troubleshooting agents from scratch. So that's what we're going to talk about today. But first, I think it's important to understand how the technology has progressed from where we were last year, maybe even 2 years ago, to where we are today. But we're going to go for it.
Thanks. But before we talk about that, I just want to introduce to you folks a new member of our team, the Cube agent. So essentially right now, we have an agent that can be responsible to troubleshoot your clusters and also auto-remediate some issues based on root cause analysis, using MCP, using Agentic. So what we're building here is not just a LLM and a chatbot, because that's to 2024. What we're doing right now is actually building an AI agent that can be your partner, that can help you to accelerate your troubleshooting and actually reduce the mean time to remediation of your issues. So what we are trying to do here is to empower network and operations center engineers so they can use those type of tools to reduce the mean time to remediation, because we know that Kubernetes is a very spread out ecosystem. So that's the idea that we have for our session, right, Sai?
Exactly. And here's the thing. We don't have anything running right now because our setup is completely clean. But we want to show you what we're going to build, just like a little bit of what's possible with the technology.
The art of the possible. So here, if you can see, we have a Slack channel, right? The Slack channel is where we're going to receive messages and everything. And then we have two terminal tabs right there. One is running a memory agent. Stick to that information to the end because we're going to build that up. And the other one is a Kubernetes specialist agent. So what's going on right now is the agent is looking to the Slack. We have received an alert using Alert Manager. And by the time we have received an alert, we have configured the troubleshooting agent to identify that alert and start to do troubleshooting based on that information. So if you can take a look, we are saying monitoring agent has been in pending state for over 1 minute. And right now, in the terminal tab, we are doing the agentic loop, and we're going to explain that later in the presentation. But right now, we are doing the agentic loop to try to fix the monitoring agent problem that we saw earlier. Now, the agent is doing the loop, executing the tools until it is able to find the last response. So let's see why the monitoring agent was actually stuck in pending state for a long time. So in this case, it's finishing the troubleshooting, doing the summary, and soon enough, we should be able to have a solution here in our thread. So of course, in this case, we're not having any human in the loop. We can have that later if we're using GitOps and everything, but just for the sake of the art of the possible, what we're showing here is that the agent got the alert from Alert Manager. It consulted runbooks that we have available in our vector database. It fixed the issue by itself because of the information that we gave to the agent. And as you can see here, we have the issue resolved. Oh, Lucas, but it's not too dangerous to let the MCP and the agent apply that stuff in our production cluster? Of course it is. That's just to show the art of the possible, but we could integrate that with GitOps and everything, but that's for later in the presentation. But that's essentially what we're going to be building today, our new teammate.
Yeah, perfect. And of course, that wasn't recording. We just wanted to show you kind of what's possible, right? Like these alert messages that can automatically fire in your Slack channel, seeing that the agent can pick those up quickly and respond with contextual information. And that's something important that we're going to dive into is, you know, we all know LLMs are just as good as the amount of context you're able to provide them. And that's even more critical for what we'll show today. So realistically, again, I love that. It's not a chatbot. That's We're at 2024. We're going into 2026. We want to go beyond that. It's not just a chatbot. We want a teammate. And you might just be thinking, oh, well, you're just wrapping chat messages in Slack. It's still a chatbot. By the end of today's session, I think you'll believe me that it's more than just a chatbot. And we're going to dive into that in a bit here. Last year, we showed RAG. This is Retrieval Augmented Generation. It's important for us to understand this because then you'll see how far we were able to come with agentic architectures over maybe simple RAG. With any sort of RAG pipeline, you have a massive set of source material. And in this case, it can be like Kubernetes logs, and of course, logs can go into the megabytes, gigabytes, terabytes, tons of data. It would be crazy to store all of that as raw data. And LLMs, they understand in a different language. It's embeddings, it's matrices. And so the first thing you do with any sort of retrieval augmented generation is you take that data source, you chunk it up, you put it into embeddings, and you put it into a vector store. So that was the first thing that we did last year. Then when the user asks a question, we take that question and we first look for any relevant context in that vector store. And so that's what you kind of see here with the context over here, is you take that context and you put it along with the embeddings from the original search. Then, now that you have the context, you pipe that into the original question and you pass it into a large language model. So, by the way, that embeddings model, this is kind of like a lightweight model just to find the relevant context. The large language model uses that context plus the original prompt, gives you a response. Let's just quickly cover what we did. Chunk the logs into vector storage. The user asks the question, why is my app response time high? You take the relevant context, you pipe it in with the original input, boom. You pass it into like a bedrock LLM, like a big agent, maybe Sonnet or Haiku, whatever you want, and you get a response.
The problem with that is, one, we are limited to the context window, right? RAG can be really intensive, and also we are using RAG here because the model itself is limited to the amount of training data that it was trained on. So now we need to inject that custom data, custom logs, to be able to do the troubleshooting. But this was last year's approach.
This was last year. And there's actually one more downside of this, of that data source chunking and storing into the vector database. We were doing that often, sure, but maybe like once every 30 minutes, once every hour. We weren't getting live data from the cluster. So if an engineer just deployed a pod and they're troubleshooting it, that data might not have been chunked and stored into the vector database yet.
And if the issue is happening right now, how we are able to reduce the mean time to remediation if we don't have live data?
Yeah, and so what we saw last year was developers would find an issue, they would go to their kubectl, they would run some commands, get the data, and then pass it into the LLM. It's like a lot of manual back and forth and context switching. And really, this is why agents are here, to kind of solve some of that. Strands is an open source SDK for building agents, and it's a fundamental way that we're going to build the agent from scratch today.
Is there anyone here already using Strands agent or have tested Strands agent? Also, I see a couple of hands raised. It's going to be good.
Yeah, perfect. No, and we're going to get into why this SDK is so good for building agents. They've really thought through the different use cases of what agents might need to do. We're going to start using some of those things as well. In addition, we're starting to see this trend in the industry of not just building one massive agent powered by one LLM, but using smaller agents that use the right LLM for the job. And so, look, really, I don't want to go too much depth into this architecture. Just know that when a user prompts this agent, that agent can use other agents. It can use multiple LLM models. It can talk directly to your AWS resources, and it can hook into MCP servers. And the way it communicates and the prompts that the agent uses to talk to one another, that's all customizable. And that's what we'll show you today with a very basic, first getting started with a basic Strands architecture. It's going to be a Slack interface that is reading chat messages that passes it to an orchestrator agent. And the reason why we use two agents here will be clear in a bit, but we use an orchestrator agent that then routes that message to another agent that's able to load information directly from the API, directly from MCP. And what you'll see is that we've pre-configured that agent to do a couple of things right off the bat. So let's get into it. We'll show the demo here. So we, again, don't have anything running just yet. And if we wanted to, I'll actually just load up the IDE, and we'll walk through some of the basic elements of the architecture. Right off the bat, I think this is the first one that we want to see.
In a little.
Here, let's do that. Cool. And
Better now?
hopefully folks can see that.
Yeah.
Nice. I think that's pretty big. Right off the bat, you can see we're importing the agent capabilities from the Strands SDK. This is all in Python, by the way. There's a lot of cookie cutter boilerplate that we have in here already that I'll quickly walk through. That orchestrator agent that I talked about, essentially, it receives messages from Slack, and it's able to do a couple of things like, right now, we configured it with one tool. Again, cookie cutter stuff, we haven't really hooked up MCP yet. It's not a very smart agent. We just manually coded this one. We say you have troubleshoot Kates, right? So let's jump into that one. And if we go into that, essentially, it'll open this file right here. This is our Kubernetes specialist. Some hints here saying we will connect it to MCP, but it doesn't have MCP just yet. So
Spoiler alert.
yeah, ignore that for now. We've actually just configured a couple of tools in here. So, oops, don't want to do that. A couple of tools here. So describe pod, get pods, and we've kind of manually, programmed these in. We'll talk about how these work in a second here. We tell the agent to use a specific, Bedrock model ID that's configured in some config settings that we'll go through here in just a second, and a troubleshoot command. This actually does the troubleshooting itself. Okay. Let's go through some of the properties that we've set up. So I think the one interesting one here was the model ID. So we're deciding to use Cloud 3 Sonnet for this one. Kind of a relatively older model, but perfectly good enough for our use case. We also have some other properties in here, like the AWS region, stuff for Slack, that kind of thing. There's a Slack handler. I don't want to get too much into this. This is cookie cutter, boilerplate code. It just takes messages from Slack, guides it to the agent. This stuff is really well documented. I think we coded this using Kiro, right? Just auto-generated this.
Yeah, I just sent the prompts to Kiro and actually Kiro code everything. I didn't even touch the code for the Slack handler itself. For the agent, yes.
Exactly. And one last thing, let's just look at the requirements file. These are all the SDKs that are and tools that are loaded, and you'll see us use these throughout. Not that many here. Fairly straightforward. Some of the Strands pieces, MCP, that kind of thing. Okay, should we do the first demo?
I think so. Let's do the first demo. And just remembering, folks, that the agent that we have right now doesn't have any access to MCP capabilities. So the only tool that it has access to is describe pods and get pods. So what Sai is going to do now is send a question to the agent with requesting information that we know that the agent doesn't have the capabilities for. But it's going to try the best to respond in the best way as possible.
So I'm going to, yeah, exactly. I'm going to ask it what namespaces are in my EKS cluster. That's me, I'm Lucas. No.
Yeah, you're Lucas.
But let's quickly take a look at the tools that we configured, right? So if we look at the agent orchestrator, we actually only had configured a couple of tools here.
Don't tools.
Describe pod and get pods. We didn't tell it how to get namespaces. It doesn't know how to. So it's going to try its best. And before I show you what it responded with, let's actually see how it kind of thought through the process. It doesn't know how to list namespaces. So first it's going to get pods. And based on that output, it's going to try and intelligently figure out what namespaces they are. Not great. It actually doesn't figure out all the namespaces. It says there's 3. And if we look at the response, it says there's 3 namespaces. That's actually not true. If we go to K9S, it's just a handy CLI tool to let us see what's running in our cluster. You can see there's actually a lot more than 3 namespaces. So we want to make it better. And to do so, I think it's maybe I'll very quickly introduce a new capability that we've just announced. I think it was last week, right?
Yeah.
And that's
2 weeks ago.
2 weeks. 2 weeks. It's the hosted EKS MCP server. Essentially, instead of having to launch the MCP server yourself locally, we do it for you. And so that means instead of having to launch a proxy and tunnel permissions and run the MCP server yourself and scale it
locally, handling 2 processes, a lot of mess.
It's all in the cloud. And essentially, it leverages IAM, so you can, identity access and permissions, so you can use that to grant the right permissions to the right set of people who should be able to use it. So let's use that. And actually, it's funny, right up until 2 weeks ago, we were doing the old way. And as soon as this came out, we thought, hey, we can really simplify the MCP configuration for our live demo. And we switched it over.
And if you're using EKS, if you have IAM permissions, you can just use it with your favorite code helper.
Exactly. And so here's that new architecture, right? So that specialist agent, you'll just notice there's one more box. There's on the bottom left there, the manually coded tools that we had from before, and then now with MCP. So now this specialist agent can decide to use the MCP if it wanted to. Let's take a look at how we would configure that. All right. We'll go back into Kiro.
We need to just switch the...
Oh, yeah. Hit the demo button.
There you go.
Should be good. Perfect. Thank you. All right. Let's jump in here, and we're going to go first to the settings file because we need a property, and a property that will essentially just tell it, hey, we want to enable MCP. So we'll enable this. Again, just looks at the environment variables and then sets it. And so now in the actual code, we'll go to our Kubernetes specialist, which, again, remember from the PowerPoint that we built this into the specialist itself, so it knows the MCP exists. First, we'll need to, actually import the system libraries from, so we import MCP, and this is essentially just using standard I/O to talk to MCP. It's a standard protocol for working with MCP servers.
And Strands 2 already has an MCP client embedded on it. So you can make your Strands agent be a client of MCP hosted servers or even local servers. It's very, very few lines of code.
Exactly. And so let me just get the spacing here right.
I think you need to align the self one all the way up.
There we go. Perfect. All right, so essentially what this is doing, if MCP is enabled, talk to the hosted MCP server. Again, obviously this will resolve to US West 2 where we're running this demo. That's a hosted MCP endpoint. One thing that we had to do in the back end was just set up the IAM role so that this app can talk to MCP and get the right info. And that's basically it. Launch the standard I/O client, and that should be good. Let me save it. Let me go back to the terminal here. Kill that Python process.
We need to add the deletion method as well.
Right.
If you don't add the deletion method, MCP, the connection will be open forever, and then we're going to have a problem. But since it's a live code session, I'm just remembering site to do that, so we don't have that issue.
There we go. So here's the cleanup step. We're going to make sure we clean up after ourselves. It's very important. Okay. All right, we're going to go back here. And again, I think you were saying this earlier, Lucas, but we're running this locally. And so it makes it easy for live demo. So we're just going to start it back up. So I killed it, and then I'm starting it back up, now with MCP. And we should see an indicator that MCP is being used now. Because until then, while we had the library downloaded, we weren't actually using it. Of course, you'll remember right up here, we import it. We added some code to talk to MCP. So now it's thinking through the process. And here we go. I think it's because I made it very big.
Yeah, just click on top of it.
There we go. Perfect. All right. Well, the spacing got messed up, but you can see it. It says
fast
MCP.
Us. It's MCP.
We're doing it live. OK, perfect. Python app is up. It's listening for Slack messages. And let's ask it the exact same question again. That's me. I'm Lucas. What namespaces are in my EKS cluster? And it's thinking. And now it should, it's using the trouble Kate's method again. And it's using a tool that I've never heard of. We haven't coded this. List Kate's resources. We don't have that. It's not in our code anywhere.
I haven't coded it.
Yeah, and in fact, it's only in the README, right? But in our documentation for MCP. But we haven't coded this anywhere. It's getting that tool from the MCP server. It talks to that hosted endpoint, and it tells our agent there's countless tools it can use, but it says for namespaces, this is the perfect one to use. List Kate's resources. It actually gets the correct set of namespaces. And now, fingers crossed, I go back to Slack, check it, boom. All right, so that's the first step. And just a few steps you've seen that we're able to make our bot that much more intelligent. It's able to pull anything from our EKS cluster that realistically the
Imagine
MCP
if we needed to create every single tool for every single possibility of troubleshooting in our agent. and would be replicating tools here and there. So what I like to think as an MCP, almost kind of an API gateway that we can centralize the communication, standardize the tools, and then reuse those tools across multiple different agents. Soon enough, we're going to be talking about how to break monolithic agents to micro agents for sure.
Yeah, exactly. I think the analogy a lot of folks have heard before for MCP is that it's like the USB-C universal plug for integrations. But I really see this as a solution for like an exponentially complicated problem. Think about all the LLMs out there. You probably use 3 or 4 yourself, and then all the tools that it could talk to. Maybe your emails, maybe an EKS cluster, maybe different AWS services. So think about it. So if you're trying to build integrations for 10 LLMs to talk to 100 different tools, 10 times 100, that's a lot of integrations. MCP is just that integration layer. So you build it once, and all your LLMs can talk to any of the tools that are built. Okay, so that takes it from an exponential problem to an ON problem. Perfect. So we've added MCP. Our chatbot is that much more intelligent. But there's actually one thing that I wanted to show really quickly in Kiro. The way that we're actually classifying when we want to respond to a message. If we look in the prompts, these are kind of the prompts that we've configured, essentially telling the orchestrator how to behave. We have some for the orchestrator. We have some from the system prompt, basically telling it its purpose in life. This agent, you're here to solve problems for us. But we have this keywords file, and essentially we use these for kind of dumbly figuring out when we should respond. So essentially, we should respond only when the keywords are in the message. And so if we asked it a question like, what version is my EKS cluster? It's actually not going to say anything.
I think cluster is actually going to say something because it's on the keywords.
Oh,
that's right. It's live demo. Let's do it again.
Let's do it again. But if I asked it, what version of EKS am I running, for example, it wouldn't actually respond, right? Because we have like this manually worded approach for keywords. And we want to be better. We want to use AI. We want to figure out when we should respond to a message. And that's because in Slack, you might have engineers talking to one another, and they might use one of those keywords when they didn't mean to. We should find the intent of what the message was about. If an engineer is talking about a problem and needs a solution, that's when we should fire up our bot. Otherwise, if engineers are just talking about their weekend or what they did, we should kind of ignore that. Keywords is one simple approach to that, but let's use AI. We're going to expand our architecture a little bit here.
Didn't change.
Oh, here we go. Okay, so we're going to expand our architecture, and in the orchestrator, we want to make it a bit more smart. When a Slack message is received, we're going to use a different LLM, Nova Micro, to classify the message intent. If it's for troubleshooting, proceed. Otherwise, exit. I think the analogy I like here is you wouldn't put like a PhD mathematician to run your hotel check-in process, right? It's overkill. You don't need that level of intelligence. You don't need that level of operations to route people to the right rooms. We want to use a more lightweight, more efficient model. In fact, because the Slackbot responds or listens to every single message in Slack, you can see how that could exponentially get more and more expensive if we're not being a little bit more intelligent about when we respond. And so that's exactly why we want to use something like Nova Micro, which is a very lightweight model that responds very quickly to respond to messages. And so now, Lucas, I'll pass it to you, and he'll show us how the magic is done.
All right. Let's take a look into the, can you please switch to the terminal? Awesome. So let's take a look into the should respond method real quick. As you can see, if there is any keyword that was found on that list that we just defined it here, then we should respond. So if you look at the list of keywords that we have, very limited amount of keywords. So we have a limited validation method that we just created. So as Sai just said, we want to do that in a much better way. We want to be able to do a smart classification. So the first thing that I'm going to do is I'm going to add a new prompt for our classification, that model that we are using, and then I'm calling that classification prompt. So if you look at this prompt, it's very, very simple. Is this message related to Kubernetes system troubleshooting, technical issues, or requests for help? Then we pass the message, then we're replacing this variable right here, and I'm telling the model, please just respond with yes or no. Remember that we pay by the amount of tokens that gets generated. So if we limited the amount of tokens that the model can generate and still doing a smart classification, should be good enough and should be fast, right? This is exactly what we're going to validate. So we have added the classification prompt. Now I'm going to go over to Agent Orchestrator and then adding some imports here. Let me just remove that import from line 5 because we don't need that anymore. So JSON, Bolto tree, and the most important thing, before invocation even. So Strands itself already has the capabilities of intercepting messages before the message actually hits the agent. So what we are going to do now is we're going to implement a method that is able to do a smart classification using Nova Micro before we send the message to the agent itself. So we don't even pay for the Claude 3.7 model that we're using on the agent. So this is what we call before invocation even. So before invoking the agent, please run this method right here. What I'm going to do now as well is I'm going to replace the constructor method here with the one updated with the smart classification that we did. So the only thing that is different than the other one is we are instantiating Bolto tree client just to be able to talk to Bedrock and do the Nova smart classification. The agent didn't change. And then here, line 41 is the most important thing. So agent hooks add callback before invocation, and then the method that I want to call, the method that I want to use to validate my message. And I'm calling that method callback message validator because it's very straightforward name to my method. What we're going to do now is, as you can see, we don't have any method called callback message validator, any function like that. So what we're going to do now is we're going to create that function and also the Nova classification function. We're going to go over those methods real quick so we can see what we are doing. So callback message validator, that's the method that's going to be called once we send a message to our agent. Then we're going to trigger classify with Nova method, passing the message, the last user message. And if you go to classify with Nova, this is where the trick is happening, right? So first, we have the classification prompt. We are replacing the message that was a variable before with the current query that we are sending to the agent. And then here is the magic. So max tokens, 10, because yes and no are less than 10 tokens. So because we are limiting the amount of tokens, we are able to get a really fast response. And because we're using Nova Micro, we can get that even faster. It's fast.
So the idea here,
some other models.
No, exactly. And the idea here is, yes, LLMs are non-deterministic. You can ask it the same question multiple times and get a different response. But there are ways you can get around this. And,
that's right.
And that's exactly what this is doing. It's making that response more deterministic. Now we know that like 99.9% of the time, I bet if you ask it this question, it's going to come back with either yes or no, and it'll likely come back with that same response. So really just routing exactly the logic that this goes through. And of course, less tokens means faster response, and since every Slack message in the channel will be sent here, it's got to be fast.
Yeah, imagine if we have a channel with 500 people, and for every message we need to classify with Claude 3.7 Sonnet, it would be really expensive. So Nova Micro here could be one. Another model that we tested was on top, a small language model on top of CPU.
That's right.
We ran that as well on our local laptop. It worked. Of course, Nova Micro is a little bit better, but I mean, if you have good enough CPUs, you can also try to do it, small language models on top of CPU, if you don't want to use like Nova Micro and anything. But going back to the code, return answer. So if the answer that the model returns is yes, we should return true. If it's different than yes, then we're going to return false. And just one thing that I want to show to you folks right here, line 53, message classification. We're going to look for that information once we test the new implementation that we have done. But before we do that, we also need to remove that dump method that we created before. So should respond, and then this one you're not using anymore. So we are not using the keywords, static keywords analysis anymore. Now we are going to rely 100% on Nova Micro with the before invocation even that we have just defined, and let's see if it works.
And I actually like that better, that we're using this before agent invocation rather than this manually implemented callback approach. You know, again, I mentioned this before, but the folks that built Strands really figured out all of the things you might need to do with an agent. So before the LLM invocation, do this custom bit. Maybe after you want to do something to format the message in a certain way. These are all the kind of things that we wanted to show you what's possible. Okay, so you're restarting the Python app?
I've just
No
restarted.
errors.
No
Good.
errors. That's a live demo, as you can see. It's completely live, so if something breaks, it's my fault. All right, so what version of EKS am I running? I'm going to send the same query again to the model, and hopefully, if everything works, if we did it in the right way, we should be able to sweat a smart classification, and we should be able to see a response, because EKS, again, was not on the keyword list. So let's send it again.
And so before...
Message received,
okay.
generating response, message classification. There you go. So if you look at this, that's the log that I told you, and the content equals yes. So before, we didn't reply because EKS was not there, but now we are replying because Nova decided to say yes because it thinks that this query is related to system troubleshooting, Kubernetes information, and everything. So now, we did the classification, and we should be able to see a response from the agent that we didn't see before, because now we are doing that smart classification mechanism, right? So as you can see here, before we didn't have the smart classification, now we have the smart classification. So let me just try to ask something random.
Yeah, we
Hey,
should
folks.
do the negative use case,
Yeah.
right?
Hey folks, hopefully it works. Hey folks, what time we are going to have lunch today? And then if we pray, there you go. No,
There we
no.
go.
All right, so
And you saw how quick that came back too. Yes, it's an API call, but this model runs that fast where, you know, and if we looked at the cost of it, it's one token or maybe a few more for the processing, but essentially, yeah. Output token 1, exactly.
output token 1. So I mean, that's how much we're paying for every execution. Again, if you don't want to use Bedrock, if you want to use your small language model, you can implement that same architecture that we have done. And as Sai said, I think these Strands folks, they have thought about every single use case that we could do. We were doing the smart classification in a different way, and Sai approached me and said, I think we already have that before, that callback handler that you can use. And then it was much easier to implement, actually. But now, before we move any forward, because if you look at the summary of our session, there's an important concept that we talk about, right, Sai?
Yes, this is something critical that, you know, and I think this is going to be the crux of what makes these agents so powerful. And it's this concept of tribal knowledge. And you know, I see this term being coined, you know, of course, the context of tribes and software engineering has been around for a while. I kind of credit that to Spotify and the Spotify model of tribes and that kind of thing.
Squads,
but essentially,
chapters.
It's this idea that the knowledge that's in a company, the knowledge it's in the hearts and minds of the people that work there. And these people are talking over email, they're talking over Slack. And there's actually a really interesting case here, an example I want to bring up. Have you folks heard of the Voyager 1 probe that NASA, they sent it out in the 70s? I'm seeing a few folks nodding your heads. Yeah. Last year, that Voyager probe had an issue. The memory chip failed, and it wasn't submitting data back to ground control in Houston. And to solve
Houston, we have a problem.
Yes, we absolutely do. And so the memory chip failed. And you know, to solve this problem, they had to bring up documents from the 70s. They actually went back and pulled out cardboard boxes full of old documentation. And here's the crazy thing. They pulled actual NASA engineers out of retirement to consult with to solve the problem. And essentially, with the minds of the people, along with the documentation, they were able to bypass that memory chip, solve the issue, and get data routing back into their ground control. And all was good, right? But that's a concept that we know and we are all familiar with. It's, you know, even when you have perfect documentation, well, there really is no such thing as perfect docs, but even when you have really deep documentation and you have the folks that are working there, you know, you really have this concept of tribal knowledge that should be stored. And it should be present in the places that your developers are already operating. And right now, for a lot of our developers, it's Slack or Teams or wherever you're conversing. And this is something that we wanted to build into the agent. Anytime that an engineer talks about a specific design choice they made, what maybe a version of the image.
A tip, like how much you should define for memory and CPU. We know that it's not really easy to define that.
Exactly, and the thing is, you shouldn't have your your superstars, right? Your elite SREs constantly being bombarded with pings of, hey Frank, like what was the version of that image you were using? Like, and look, we want all of us to be as efficient as possible in the workplace, and so when these conversations do happen, let's store them. Let's store them in some sort of knowledge database that can be accessed when that question, inevitably comes up 3 months down the line, or in NASA's case, 50 years down the line, right? So we want to store this type of tribal knowledge somewhere. And to do so, we're going to expand our architecture a bit. So this is what we had before. And to add tribal knowledge, we're going to leverage an all-new capability that we announced back in July, S3 vectors.
So if you are thinking why they are using two agents layered on top of one another, now you get a response, because we're integrating multiple agents. And if we have all those use cases in a single agent, trust me, I've tried, it would take much more time to respond in the right way, and hallucinate would be a problem as well.
Yeah. Up until now, that orchestrator agent was just taking the message, figuring out if it's relevant, and then passing it to the specialist. But now we actually have kind of a branching approach of, first, we have to think about, is that message, is it actually for troubleshooting, or is this just a tip that we should store away for later use, right? And the cool thing about this is, the longer it's implemented in your engineers' Slack channels and wherever this agent is listening, the smarter it gets. It's storing these solutions for future use. Essentially, anytime there's some information being shared in Slack, automatically take it and store it in vectors for a future recall. Oh, and by the way, vectors, again, we talked about this quickly before, but it's a type of database that works nicely with LLMs. Of course, LLMs don't think in terms of tokens. They work with embeddings and number matrices and transformers. And so vectors are a very efficient way of storing human-readable text, right? So you take a bunch of human-readable text, you encode it into embeddings, and then when the LLM needs to scan through that data later, it's a lot faster to go through a vector database. But then it's able to kind of reverse engineer that back into human-readable text and give it back to the end user. So this is how we're going to expand the architecture. And let me pass it back to you, Lucas.
And we have not, and one thing that I just want to add on what you said, Sai, it's not either an agent or either an MCP. It's more a combination of different tools and capabilities to empower the agent that you can use. So we're using MCP for the live data, right? So the data that we need in that time that is happening right now in my cluster, then we use MCP to do it. But maybe some tips, runbooks and everything, we can still rely on RAG. We don't need to use MCP for that. We could, but in this case, we're using RAG on top of another agent. So it's a combination of everything. It's not like if I use MCP or agents, I'm not going to use RAG anymore. I think it's what is best for your use case, and like every other essay probably would say, it depends on the use case. Yeah, so let's try to implement the memory agent right now. Hopefully it's going to work. So the first thing, the first thing that we're going to do is, actually, Sai told us that we're using another agent. So we created that memory agent to be a standalone agent because other agents could rely on that memory agent as well. So I've created a Kubernetes troubleshooting chatbot. Maybe Sai is creating a database analytics troubleshooting chatbot. But we are saving and storing the information maybe in the same place, and we can reuse those runbooks across multiple agents. So the agent that we're going to be building now has a server embedded that's powered by Strands, and then we're going to integrate that agent server with our current structure that we have, orchestrator plus specialist, using A2A. And for those who don't know, A2A is just a way to communicate with different agents, JSON over HTTP. Essentially, it's nothing more than that. But
agent to agent.
Agent to agent. Yeah. That's it. Really easy to understand.
So Lucas, I got to say, man, as you're going through that, it sounds a whole lot like the 12-factor app, microservices spiel that we heard, like 12, 13 years ago now, in the early 2010s, of why we break monoliths into microservices. It's really the same. It's kind of this revolution. It's this cycle of programming, and it's the same reason why we're breaking our agents apart, because, look, the memory agent has its own purpose that might be used outside of the context of this Slack bot.
Just like a microservice, right? What is a microservice? Something that should do that use case in a very good way, and then if you want to add other use cases on top of that, then maybe we need to start to think about creating a different microservice. So for the agent, it's exactly the same thing. The agent should have a purpose. We tried to have everything in a single agent. The response was really, really awful. Once we break it down, and then we use the agent as tools pattern with the orchestrator agent, we got a much better response and performance on top of the agents that we are developing. So specialist agents, that's what I want to say. So I just have pasted the code right here. I'm going to go over the code that we are building. Again, it's yet another agent, so it's just more of that other code that we have running. So we have the constructor method. We're declaring some variables. We are initializing Boto3 client to talk to our S3 as vector database. And then we are defining a system prompt. So essentially, the system prompt is what you are giving to the agent. You should behave like that. You are an agent that behaves like that. So you are a Kubernetes troubleshooting memory specialist, and then your role is store solutions and retrieve solutions. After that, it's all like some fixes and don't like use Markdown and everything, but two main tools that we have is store and retrieve. And then using Strands, again, we are defining the agent, we are defining the model that we want to use.
Lucas, I just want to point one quick thing out. That you look at number 3, and some of you might be thinking, only do what you do and nothing more. It's very direct. You might even consider it to be rude, but we've seen official research papers released on when you start using words like please or asking nicely for agents, they actually do end up hallucinating more often and not retrieving solutions and responding in the right way. So,
and if you say please, you're going to pay even more for the tokens that you're sending to the model. So
exactly. So you do want to be very direct with these models, and they behave better when you give them those tight bound lines.
Try to imagine that is a co-work that you don't like and be very bold. Don't do that. Don't do that. All right, so the agent, Bedrock Model ID, 2 tools. I'm not going to go over all those tools, but essentially, it's 2 tools only, but I'm not going to go over the code because I don't have a lot of time. So one tool is to store a solution. What it does, store solutions in S3 vector database, and the other tool is to retrieve a solution from vector database based on a query.
Lucas, question. Do we have to do the conversion into embeddings, or does S3 do that for us? How does that work?
About to say that. So S3 will not embed the data for you. You're going to need to embed the data. So essentially, embedding is just make the data in a way that the model can understand and interpret that data to respond back to you. So for S3 vectors, it's just a vector database. We still need to do the embedding. So in this case, we're using Amazon Titan on top of Bedrock to do the embeddings. And once we embed, we cannot de-embed the embedding data, right? So what we need to do is we need to embed the query that we're using to retrieve. So in this case, the store, let's go to retrieve. We need to embed the data that we're using to retrieve. There we go. And then once we embed the data that we're using to retrieve, we can search for the embeddings because we cannot de-embed an embedded query. So we need to embed using the same model. And because we're using the same model, you can use that chunk of data to search for similarities in our vector database.
That's exactly right. And it essentially, we talked about earlier, you don't want to store the actual human-readable text because it takes a lot longer to scan through it and find relevant data. It's just faster when you're embedding. And Lucas, how many LLMs are we up to at this point? Is that our 4th? Or I think that might be the 5th. We're using Sonnet. We're using Nova Micro. We used a different version of Sonnet for the memory.
Titan for embedding, so far 4 different models.
Exactly, and look, this is how LLMs are meant to be used. You pick the right one for the tool, and it's more efficient.
And every agent that we had there could also use a different model. We're just using the same model for the purpose of I just want to export one single environment variable, but we could use different models for different agents with different purposes. So for instance, Cloud Haiku is much faster than Cloud Sonnet 3.7. But it's not as smart as Cloud Sonnet 3.7. So we need to do those balances and try to pick the best one for our use case. But in this case, we have the memory server. Again, we have 2 tools, one store and the other one retrieve. And now what we're going to do is we're going to launch an agent server. But before we do that, I'm going to actually try to use those tools manually. So what we're going to do is I'm going to get the variable that I have here from a class. I'm going to call agent, and I'm going to say something like,
so this just invokes the agent as if, imagine the orchestrator agent was talking to the memory agent. We're just simulating that for the sake of testing. And so we're calling the agent directly. And yeah, okay, so we're doing a real example. So Lucas is copying over a real model recommendation that we have for the node exporter image.
So what I'm saying is anyone deploying monitoring agent should use this image. If you watch at the hook of our presentation, you probably know where we are going with that information, right? So what we are doing now is we're triggering it manually first. So hopefully this query right here is going to trigger a store, and then we want to create another query, another agent invocation to retrieve the solution. So what I'm going to say here is, what node exporter image should I use?
And these run synchronously, so one after the other. So it'll give it time to store the solution.
Yeah, so essentially the first one, we're not telling which tool to use, but because we are using an agent, it should use the store, and the other one should use the retrieve. So what we're going to do now is I'm going to go to the folder where we have that agent created. There you go. So we have the memory agent server.
And you can already notice the difference here. Before, we were just restarting that one Python application, which had the orchestrator and the specialist agent. Now we have a separate memory agent that lives separately. So it is its own microservice. Lucas, you came up with a word for this earlier.
Micro agent?
Micro agent. You heard it here first, folks. And so, look, by the way, we do give you Helm charts to deploy all of this, and all the sample code as well we'll share with you at the end. So you could deploy this in a Kubernetes cluster so you're not doing it manually locally. I think it's just for the sake of the demo, we're doing it.
Yeah, we are doing it locally because it's a live code session, but it's all abstracted into Helm charts. So if you just want to take the shot and deploy this architecture, you can. We're going to give access to the sample code for you at the end. But going back to what we are doing, let's try to see, Sai, if the tools are going to be able to be executed in the right way. So we are hoping to get store and then retrieve the node exporter tip. So I just triggered the memory agent.
And you commented it out so that the server isn't starting.
No.
We're just calling the agent synchronously just to test.
Yeah, so the first two, store solution, key information, problem 10 is using consistent and corrected image. That's the image that you should use. And then for the second tool to retrieve the information, there you go. So the DevOps team recommendation is that one. That is the one that we added into the code. So now we have that information in our S3 vector database. So what I'm going to do now is I'm going to go to a dashboard that, of course, was completely generated by AI. And then I'm going to refresh it. And then we should be able to see another solution. That dashboard is just querying S3 to check the solutions we have available in S3. But as you can see, we have a total of one solution in that particular bucket. If I search here for node exporter, we should be able to see the solution that we just persisted. So teams using consistent and correct image for node exporter in Kubernetes monitoring deployments. That's the image that you should use. So we have that in the vector database right now because we tested locally our memory agent. So what we're going to do now is we're going to remove those local executions that we have just done. And then we're going to now, start the A2A server. So if you look at here, we have the A2A server. That is essentially a library that we have imported from Strands multi-agent capabilities. We're passing the agent that we want to run as a server, and then we do a serve. Behind the scenes, it's going to start a UV-corn process. So if you do Python memory agent server.py, now we have agent running as a server. So if it's running as a server, you can expose to a load balancer, and now you can use that agent with your other agent. So you don't need to replicate that memory agent code again and again and again. So that's it for now for the memory agent server. Now, what we're going to do is we need to make the orchestrator agent communicate to the memory agent server, right? And for that, we're using A2A. So what we're going to do now is we're going to implement that A2A communication on top of our agent orchestrator. And remember, for the agent orchestrator, we are running the agent as tools patterns. So we have an orchestrator agent that is calling other agent as tools. So if you can see here, we have just the troubleshooting Kubernetes tools that will trigger the Kubernetes specialist agent. What we're going to do now is we're going to create the memory agent tool that will talk to the other agent running its own server using A2A. So the first thing that we need to do is we need to import the library that we want, so A2A client tool provider, and this way we are able to use the other agent tools in our own agent without replicating those tools in our code. So this is the first thing that we need to do. Now, another thing that we need to do is actually create a tool. Since we're using the agent as tools pattern from Strands, we need to also create a tool to talk to our memory agent. So I'm going to copy and paste the method that we have created here. And as you can see, I have a decorator here. So this is particular for Strands. If you have the decorator on top of the method, you can use that method as tools in your agent, right? So that's the way that the method is able to be identified as a tool. But most important thing, A2A client tool provider, that comes from Strand, and then I'm passing the memory agent URL. If you can see here, port 9000, that's exactly the same port that we have here for the memory agent running as a server. So we already have configured that variable. And then what I'm doing is I'm creating that agent here, and this agent is just an interface. So we are using this agent to discover other agents available in our environment. In this case, we just gave one single agent. But if you look at here, we have a list. We could pass multiple different agents, and our agent would figure out which agent it should call. How many times I said agent right now? Like 70 times.
I'm going to say it a couple more times too, because I think it might be worth really quickly. I'm going to switch here to the Strands agent architecture, just to show you what we did, right? So we have that orchestrator agent. That's that big box over here. And it kind of is able to discover all the other tools it's able to work with. So this external tool / AWS, that in itself can be additional agents. That in itself is the kind of swarm we're building here. Strands likes to call it swarms, but essentially it's all of these different agents that are discovering each other and only talking to them when they realize you need it. And so I think that's really the idea here is you can have all of these different tools, the MCP server that we deployed, this memory agent, and then we have this actual Kubernetes specialist agent. And realistically, it's hard for us to even code like an if-else chain of when which one should talk to the other. So we offload that responsibility in itself to an agent call.
Shift to left. Remove from if and else's and send to the agent.
Exactly. You got it. All right. So let's get back to it and see how you did it.
All right. So that's the memory agent provider. That's my tool that's going to talk to our agent server. Last thing that we need to do is we need to add that tool.
You were saying earlier, it's the agent as tool kind of paradigm. That's essentially what we did. We took an agent and we threw it in there as another tool. Just like we did with MCP and the troubleshooting stuff, we just threw it in there.
Yeah, so if you look at Strands, that's actually a pattern. Agent as tools, that's the pattern that we are following, and then we are adding A2A on top of that as well. So that's essentially what we are doing. We have an orchestrator agent that is responsible to route requests to other specialized agents. So now let's go back. I have added already the memory agent provider here as a tool. So the last thing that we need to do is we need to change the system prompt. So let's go to the orchestrator system prompt. And then if you look at the system prompt, we're not saying anything about memory or vectors or whatever. We're just saying like, we have access to that Kubernetes specialist agent to troubleshoot. That's the one you have. Go for it. Now what we are doing is we're going to replace that orchestrator system prompt with something more aligned to the memory agent that we have created. And for every agent, we have a system prompt. So in this case, I'm saying, hey, always check memory first before doing any troubleshooting. If you are not able to find memory, then go and troubleshoot. If the information is good enough, then persist that information for me after you are done with the troubleshootings. And again, we can control that. We can split responsibilities here. We can make the agent fix. Of course, we don't want to do that in production. If we're talking about production, we can make the agent open a pull request for a GitOps repository. And we already have that. If you want to see that, come back to next year code session. But for this year code session, we are doing an orchestrator agent and then just passing the prompt here. So now what I'm going to do, and hopefully everything will work, I'm going to trigger our main agent. That's going to be able to talk to the other agent running as a server.
So I see now you've started them up as two separate processes. One for that memory agent and one for the actual main orchestrator plus specialist. And so think about this. If you were to deploy this in Kubernetes, for example, you could deploy each of these as individual Python pods and also scale them independently of one another as well. For example, the memory agent has to respond every single time a message is pasted in Slack, whereas the troubleshooting agent doesn't need to respond as often. So you could really scale in response to demand and load.
Yeah, so let's see if it actually worked. So what I'm going to say is, I'm just going to try to trigger the agent to persist a tip and advice that some of our DevOps engineers have done. So what I'm going to say is, if you don't know how much CPU and memory define for your limits, always define the same as requests. And that might be true, right? So that's a tip that I'm giving, and I'm going to say tip from DevOps Squad. So hopefully, we're going to be able to classify this message. The agent should respond to this message because it's related to troubleshooting. Okay, as you can see.
We didn't fix the classification, did we?
We didn't fix the classification.
That's right. So the classification should know. Right now, if you look at the prompt for the classification model, let's take a look at it really quickly. If it's related to Kubernetes, system troubleshooting, technical issues, I bet if we updated this, and let's make it a little smarter, if you have any tips to store, right?
You want to do that?
Let's do it.
We haven't tested this.
Let's try.
Let's see if it. I think it's going to work. Let's see. Is this message related to Kubernetes or request for help or any tips? Is it good enough?
Pretty good.
If it doesn't work, I'm going to tag the agent.
That should cover all the tips, but if we wanted to get more precise in the future for troubleshooting tips or something like that, we could add that. For now, we're doing it live. We want to make sure that classification responds yes for a message like that.
If it doesn't respond yes, then I can tag the agent, and you can be sure that this is a live demo. Right, so let's wait for the Kubernetes specialist agent and orchestrator agent to start. There you go. Now, I'm going to send exactly the same message. And if we did it in the right way, we should be able to see yes.
Come on, demo gods. One time.
Yes!
There we go. See? So here's the thing. Again, it is non-deterministic by nature. That's how LLMs operate. But you saw with just that little bit of prodding, of like changing that classification prompt, we were able to make it respond better for something like this. And so we're not saying you're going to find the perfect prompt that fits your use case immediately. Like, of course, for example, OpenAI has been refining their prompts and prompt engineering their base models for years now. You're going to want to keep optimizing. And with that small optimization, the classification worked.
And then if you can see, the agent, they talk to each other. So first, we send a message to discover the agents that we have using the agent card that is available in our agent. So if you look at here, we use a H-way list discovered agents, and then we discover the memory agent. And then with this, we also discover the tools that the agent that we are talking to have. And now we are sending a message to the right tool. We send a message to store solution in our other agent running as a server. And if you can look at here, we have one tool that was called on the memory agent that was to store the solution related to QoS guaranteed. Essentially, same amount of CPU and memory resources. And then, there you go, you have a response here.
Okay, and by the way, I think in the real scenario, it wouldn't even respond. The bot would just sit there silently listening for any tip and just storing it in the database. But for the sake of the demo, we have it respond saying, hey, this is a good tip. We'll store it in the database.
And if you're not trusting me, we had one solution before. Let's refresh it. Now we have a total of two solutions. Let's search for CPU limits and see if we have that solution there available already.
And so this is going directly to the S3 vectors database, right? Just looking at what solutions we have.
Yeah, absolutely. So that's the same. I'm doing a RAG here in the same way that we are doing for the agent. So we are like just retrieving, embedding the query and then retrieving the solution. So that's the solution with the shortest distance. So essentially that's the solution that means the most for our use case right here. So if you can see, please define the same amount of CPU and memory that you have for your servers. That's great.
It's like a confidence rating, right? It's like the inverse of a confidence rating. So smaller distance means more confident. And I think you saw that second solution was at a distance of like 0.9. That node exporter tip, not very relevant for the question that was asked about CPU limits.
Yeah, so last thing that I'm going to try to do, I know that we have just 5 minutes. So what I'm going to try to do now is I'm going to deploy some failing pods. And remember that first demo that we saw before, fixing the memory, the monitoring agent, that's essentially what we're going to try to do now. So let me deploy the failing pods to our cluster. We should be able to see the demo app namespace here.
And you still have the Python main orchestrator running, right? Or did we kill that?
No, I killed that, but I'm gonna make it run again.
Okay, cool.
But essentially, we have the pods not running. Let me just trigger the agent again, agentic troubleshooting. And then I'm gonna trigger the agent again. There you go. So now, if you look at this, we have a lot of issues going on. We have the monitoring agent not working. We have the back-end API restarting with out of memory killed. Front end has some issues as well, and then we have a Redis here. Let's try to debug and fix the monitoring agent using the recommended image that we have stored in the solutions. So before we do that, let's see if the agent has started already. Both apps running. There you go. So what I'm going to say is, hey folks, my monitoring agent on demo app namespace is not running.
You know, there's usually...
I'm a developer. I don't know why it's not running.
And you know there's usually some poor SRE that's always in this channel having to respond to these kind of messages. This guy who's probably overloaded with too many messages. Maybe it's some of you in this room can relate to this yourself. Hopefully the agent can pick this up and not one of you, right? Love the emojis. Let's see.
I just tried to see if it's going to fail or not, but there you go. Yes. So the first thing that it's going to do, because our system prompt, it's going to search in our vector database to see if there is any solution related to this. Hopefully, we're going to get the right image because that's related to node exporter. There you go. So the first image, the first solution, the closest one to what we search is the solution number 1. So it was able to get in the proper way, but it's not enough information. So what the agent is doing is actually doing the troubleshooting by itself with that information in mind. If we had more information, it would use it. So
I actually love this question you asked because it just demonstrated all the features we developed. On the left side, it found the 2 memory solutions. It realized this isn't relevant. Then it went back to the original specialist agent, talks to MCP to get more information about what's failing. MCP gives it all the application logs and the pod logs. And you can see it all thinking, all orchestrated together. And ideally, figures out what the original problem is.
Yeah, so right now it's just storing the solution because it was able to find the root cause. So if anyone deploys that agent again with that same root cause, we don't need to do the troubleshooting again. We can go straight to the issue. So our solution...
That's actually really cool. So it found the solution and decided to store it in our solutions database?
Yeah.
We didn't even have to code that in there. It realized it
yeah.
and decided, well, let's just store this for future uses.
And if you look at this, we didn't got the response that we were expecting to get. So let's try to ask that again. What is going on? What is the issue?
You know, we've seen this before. When it stores the solution in the database, it considers itself done. It's like, found the solution, stored it. We don't have to respond. But
there you go. Since we still have the context on the threads and everything, it responded super fast. So essentially, the root cause is we are using the image non-existing monitoring agent.latest. Of course, this image doesn't exist, so would you like me to guide you through the steps to fix the issue? No, I would like you to fix the issue. So I'm going to say, Kate's Magic Bot, please, because you said that you don't want me to add in please, so I'm going to say please because I watch a Terminator number 2, so I'm going to say please. So please, can you fix the monitoring agent for me using the recommended DevOps image?
Okay, while this thinks, Lucas, because we have 15 seconds left, folks, I want to share with you some resources really quickly. So scan this QR code. It's going to take you to a GitHub of all of the container sessions that we're doing at reInvent. So find our session here. So with CNS421, find our session, and we'll have the sample code. We'll have all of the code that we showed today linked as well. It's all on GitHub for you to go through. We really appreciate you spending your time here with us today. So scan that QR. You'll find all of the relevant resources there. And we would love for you to leave us some feedback in the app as well. Thank you so much.
Hold on. Can you go back to the demo? There it goes. So now we have the monitoring agent running, as you can see right there. And then if we go to alert managers, There we go, resolve it. The same day. Yeah, we deserve it. Thank you. Thank you so much.